This is the AstroCom Advanced Solar Tracking and Rover Observation Communication project in our CDR. This project is sponsored by FSI, the Florida Space Institute, and we do want to thank them for their support. The motivation for this project was to help researchers explore the south pole of the moon. One of the issues that are faced with the exploration of the south pole of the moon is the angle of the sun and how it doesn't illuminate certain locations. The lack of infrastructure on the moon also limits exploration, as there's a limited range of communication to these craters and other permanently shaded locations. So our project plans to address this with two different solutions. The first being a heliostat tower to reflect light from the sun into these permanently shaded spots, and it would be equipped with some communication capabilities. And then another tower that would be a smaller communication beacon that could be carried by the rovers to form a communication network with the rovers and be able to communicate data back from these craters and other locations. Go.
A quick explanation about the mechanism of the whole mirror towers is, first we have the stepper control the W axis with turning the whole tower left and right. Next we will have a tripod to hold up our mirror, which can be adjustable by increase and raise the mirror to a correct height. Then we can have a mirror which composed of a plexiglass cut in a round circle and covered by mylar. So with this mirror, we can clearly see that it has a really high reflection using a high amount of light, and it's similar with sunlight we have been recording outside. Lastly, the rotation of the servo, as explained before, will depend on the 3D printed joint and housing. With the tower, we have a big plate, and the plate will be rotated using a gear mechanism, and underneath the plate there are support to use a bowl roller to support the weight of the whole tower to prevent any bending. And underneath the tower is the stepper, which connect through the slip ring, and this is the stepper and the stepper housing. That's pretty much it about the stepper. The stepper and the MCU can be put into its housing using a groove. This is housing for stepper, and this is housing for the MCU. The stepper will be running on a 12 volt and approximately 3 amperage.
Okay, so now we're going to do some live tracking on the rover. So it's on target 1 right now, which is this rover. And what Alex is going to do is going to move the sun, and this will live track the sun and direct light onto our target.
Sun is already point in the position. Here's some specification that we plan to meet with our projects, especially the response time, the maximum response time when the mirror is moving and receive a request is at most 3 minutes. The powers that can sustain both the heliostat tower and the communications tower should be sufficient to be able to run for a long time.
So here we have our solar panel, which is going to be providing all the power to the AstroCom heliostat tower. As you can see right now, it's currently providing 2.6 amps as the short circuit current. If we check the voltage, it should be around 20 volts in open circuit, which is well over 50 watts. Obviously, these are the best case values. Make sure you're in DC. There we go. These are the best case values under actual conditions. It'll be a little bit less efficient than that, but again, it'll be well over 30 watts supplied. And now I can tilt the panel up as well and show that the current actually increases as the panel becomes closer to perpendicular to the sun. And that'll be the state that our tower is in. It's much closer to perpendicular to the sun's rays.
So now we're going to test the response time of the Zigbee communication, which is going to test how long it takes from when we push the button to send the signal to change the target to the mirror actually moving.
So I'm going to push the button right now.
So that response time was about 3-4 seconds. We're going to do it one more time.
You just pushed it?
About 4 seconds again. One time.
Just push it again.
That was about 5-6 seconds. So as you can see, our response time is about an average about 4.5 seconds.
All right, so this is our communication tower here. We're doing the test to show how much power it draws while it's running. So as you can see here, this is measuring the current from our current probe, and we're getting values less than 2.24 milliwatts at 0.1 volts per amp, which means we're drawing less than, I believe, before I speak here, let me measure. That many milliamps, right? And we're running on a 12 volt power supply. So if we multiply this number, we get 2.7 watts approximately. And we can also prove this is during communications as well. If Pedro presses the button, we can see communications are received on the other end, and our peak value never exceeds that 2.24 millivolts here. So the current draw is below that value, so it should be all good. So this is our MCU board. In the upper right hand corner we have all the regulators and the ICs for the regulators. I'm going to go ahead and power up a 12 volt power supply here and connect the board to the 12 volt. You can see both the 5 volt LED and the 3.3 volt LEDs are on, indicating that this board has both 5 volt and 3.3 volt lines active. This serves to power both the MCU and a few accessory components connected over USB-C and USB-A. We also have a strapping pin switch to select whether we want to boot or if we want to run the MCU normally. We also have a reset switch as well as a pull down switch on a separate GPIO. We also have a plethora of jumpers out for all the IO slots, as well as some communications there. Initially we're going to include an SD card connector, but we scrapped that idea as the SD card wasn't necessary for what we intended to do. Looking at our USB-C slots, on the right hand side we have the stepper switch, the servo switch, and then a laptop, connectors rather. So this is a laptop connector there where we can boot code to the ESP as well as monitor the code that's currently running. We also have an accessory 3.3 volt regulator there, so that way we can run the 3.3 volt line from just the laptop, so that way we don't need to power the board with 12 volts every time we want to boot new code. However, I have isolated that as we don't want those regulators competing with each other. We also have the USB-A over there that'll connect to the sensor board that we'll see later, and that runs over I2C to read all the sensor values.
So this is our servo board. It will use to be controlled 3 different servo, X, Y, and Z. The first servo will control the movement of the sensor housing. The second servo will control the x-axis of the mirror. The last servo will control the y-axis of the mirror. Through these 3 servo will run through a mux using I2C, which connect to the MCU's board, which this regulator right here will take in the 5 volt input and will regulate to 3.3 and control the mux. We also have a connector using USB-C to connect to MCUs, which will run to use the I2C. Right now, the regulator is connected externally to a 5-volt source, which can be seen by the LED that this board is turned on.
So this is our sensor board, and the sensor board has 5 different VEML 7700 sensors that work with the sensor multiplexer. And how this works is it comes through the I2C data line through this USB-A cable, and it will be able to read from each sensor individually as it goes through its reading values and reading functions. And these values will be tested against each other to determine to move this motor vertically or also move the stepper horizontally. And this works because it has the partition, which gives it dividers so that light can't hit all 4 sensors at the same time if it is off. But once it is directly on the source, it should theoretically have all of the light values be the same.
All right, so this is the charge controller we're using. This is going to take the DC from the solar panel here, which is typically going to be about 24 volts. We're inside, so I got that simulated with a 24 volt power supply. I'm not sure if the figure comes in there.
That's good.
All right, but this is going to charge the battery and also allow any subsystems to run off the 24 volt from the solar panel, but it is going to step it down to 12 volt. Right now I'm connecting our lithium iron phosphate battery. It's typically 12 volt. I'm going to plug that in, and then we can see the current on our power supply just increased because our battery was drained. So it's now charging our battery there off of what typically would be the solar panel. Today we're simulating it with the power supply. I also have a multimeter here just to confirm that it is indeed outputting 12 volts for all our subsystems. Sorry, I got my probes a little mixed up here. There it is. About 12.6 volts, which worked just fine.
All right, so this is the communication tower part of the project. So in the final version of the project, this coordinator dongle here will be running on the rover, but for demonstration purposes, we are showing it with hosting the coordinator through this Raspberry Pi over here with this dongle. If you look inside of the comm tower box here, we are running a battery that's powering this microcontroller, and this microcontroller is working as an end Zigbee device. So when I push this button, it can send a signal that will tell the tower to do something. In our original software design in the paper, it was said that this box would function as a intermediary device that could extend communications. It can still work that way if we use router firmware in here instead. But currently this is the best way to show we can send messages using wireless and control our devices. So to demonstrate this working, I'll run npm start here, and that's going to be able to show the MQTT console, which is the messaging protocol that we're using here that communicates with the Zigbee from the native and Zigbee device. Alright, so now once it's starting, you can see that we have published this message saying that our device is called Flashbang. So this tells it that this Flashbang here is on the network. We can also verify this by going to the front end here. So here is Flashbang. He's here. The connection is perfect, and it's working as an end device. So once you actually go in here and push this button, you can see the message comes up. It receives the Zigbee message from Flashbang, and when the entire system is online, this controls our tower movement, and this message can also be seen from the rover's mobile app. So it's the comm tower demonstration.